Welcome. This question says a sphere of 2 kilogram per cubic meter density floats on the surface on a liquid that has a density of 8 kilograms per cubic meter. Show that 75% of the sphere's volume is above the water. So not the way I've drawn it here. This is just a schematic diagram. We're actually trying to show that it would be more something like this. And we're trying to show that this here is 75% and this there is 25%. Okay, so where do we begin? We begin by thinking about what we know. What we know about floating objects when they float on the surface is that they are in equilibrium and therefore their buoyant force must be equal and opposite to the weight of the object. So I can say, oh, the buoyant force is equal to the weight of the object. And then I can say, well, what is the expression for the buoyant force? And it's going to be the density of the fluid. It's all about the fluid times G times the volume of the displaced fluid. And this is going to equal, well, the weight of the object is just the density of the object times G times the volume of the object. Whether it's inside the fluid or outside the fluid, it's the volume of the object. Now, what I want is a ratio between the volume above the surface of the fluid and the total area. And it turns out that's not so easy. That's not the easiest part to get. The easiest part to get is to get the ratio of the volume under the fluid to the total volume of the object. Because if you look at this, the volume under the fluid is the volume of the displaced fluid, and the volume of the entire object is the volume of the object. And if I look back at my equation above, both those terms are in that equation. So if I simply rearrange that equation, I can get, well, that's the density of the object times G over the density of the fluid times G, just by rearranging this equation here. G's cancel, of course, because they're on top and bottom. So this is simply the density of the object over the density of the fluid. And if I put numbers in, the density of the object is 2, and the density of the fluid is 8. So my volume of the displaced fluid over the volume of the object is equal to 0.25. Let's go back to our diagram. The volume of the displaced fluid is the bit that's under the water, and the volume of the object is the entire, in this case, sphere. I'm asked for, show that the 75% of the sphere's volume is above the water. So I'm being asked to compare this with the entire shape. So it's just another step. I say the volume above over the volume of the object is equal to, well, it's going to be the volume of the object minus the volume of the displaced fluid. It's the volume of the entire object minus the volume of the displaced fluid, that's the volume above, divided by the volume of the object. So this equals 1 minus the volume of the displaced fluid over the volume of the object. Just doing a little bit of math there, which is 1 minus, I just worked this out. This was 0.25. So mathematically that equals 0.75. That's the fraction of the whole volume that's above the fluid. And I can express that as a percentage. And 0.75 of 1 is the same as 75 of 100. So that's 75%. And that's what I was asked to show. So we visualized, we recognized that the conceptual underpinning was that for objects that are floating on the surface, the force of buoyancy, the buoyant force is equal to the weight, equal and opposite because they're in opposite directions. I then expanded those two terms, and I recognized this is again is something where you might not recognize it when you start the problem, but I recognize that the volume of the displaced fluid over the volume of the object was simply was a fractional volume, which is what I was interested in. It's not the actual final answer, but it's the alternative question. So I rearranged my equation and found a very simple solution, actually. It's a bit surprisingly simple. And I could have asked you for what is the percentage of the sphere's volume is below the water, and that would have been my answer as a percentage. But here I'm asking you what percentage of the sphere's volume is above the water, so I have to recognize, well, the volume above over the entire volume is equal to the entire volume minus the volume below over the entire volume, and then let the math take care of itself. I find this type of problem, the first time I tried one of these, I thought this is going to be amazingly difficult. And yet if you stick to your principles, you can feel your way through the problem. And it's one of those things where once you've seen it, you kind of know where you are. So there we have it.